Hello everyone. So let's practice for the paper 5 of the CIE A-level physics, which is the planning, analysis and evaluation question paper. So in this video, we're going to practice with the planning part of the question. That is usually question number 1, planning question. So this is May, June 22, 51/53 because the two variants are identical. Okay, so let's see. A student investigates the current in a coil and a resistor connected in series as shown. The student connects a high voltage DC power supply and a switch across the series combination. When the switch is closed, it takes time t for the current in the resistor of resistor R to reach a maximum value. The time t is a few milliseconds. There are a number of different unmarked resistors available. Now, if you notice this one little thing over here, the time t is a few milliseconds. So when we're measuring this time, we can't measure this with a stopwatch. We need to have something with recording capability and high resolution so that it can record across a few milliseconds. There are a number of different unmarked resistors available. That means we have no way of knowing which one is bigger, which one is smaller without actually, putting it on the ohm meter. It is suggested that the relationship between T and R, time to reach the maximum current and the resistance R, okay, is T is equal to Kn squared A and R, where N is the number of turns of wire on the coil, and A is the cross-sectional area of the coil, right? And L is the length of the coil and K is a constant, right? Okay. So design a laboratory experiment to test the relationship between T and R, right? Explain how your results could be used to determine a value for K. Now let's go with the diagram and see what we can include and what we can't include. Now this is the experimental design that I have chosen for this. Yours could be different. It could be a little bit simpler. Since my purpose over here is to illustrate everything over here for clarity. So that's why I've included quite a lot over here. But your design could be simple. So, however, let's talk about these things. This is a switch and DC power supply that we were asked to include in the circuit. Resistor and coil are the same as before. However, the method for measuring the current or the time to reach the maximum current, for me it's different, for you it could be different. You could add an ammeter with a data logger. Over here, what I'm going to do is I will measure the outputs or monitor the outputs using storage oscilloscope that can record for a while, and then we will analyze how much time it takes for it to reach the maximum voltage. So maximum current passing through the resistor will produce the maximum potential difference also. So we can measure the time. We can't measure the resistance of a resistor with an ohm meter when the current is on. Okay, so we need to have a separate circuit for that, for measuring the resistance using ohm meter without the power supply when no current is flowing. Okay, since we also have to deal with the length of the coil, diameter of the coil, so we need to have methods to measure them also. Vernier calipers can be used to measure the diameter, which can lead to cross-sectional area. Ruler simply can be used for the length, and additionally we will have to come up with how to count the number of turns. So this will just be counting basically. We don't have to measurement tool for that. Okay, now some sections for this, like how we are going to start, is problem definition or defining the problem. I'm sorry. Then we will have methods of data collection, or simply measurements. Okay. Then we will need the procedure or methodology, basically, analysis, and finally safety precaution. All right. Now let's start off with the defining the problem. So obviously this means that we need to decide what is going to be our independent variable, what is going to be our dependent variable, and what is going to be our control variable. Okay, so let's go back quickly to let's see what they said. The relationship is between T and R. So T is the dependent and R is the independent. Right, okay. Going back, independent variable is the resistance R ohms of resistor. Dependent variable is the time T for current flowing to reach its maximum value. Sorry. Okay. Now control variable. Control variable, the rest of the items will be control. Length, L, diameter, D, or in short you can say cross-sectional area also. And number of turns of the coil, number of turns N of coil. Now all these things belong to the coil, like the properties for the coil. Then we will have also the supply voltage E, and what else? Yes, this one. T and R. So we have, this is the number of the turns, cross-sectional area, length, and resistance. Actually, let me just simply copy this before I come back again. So I will, paste it over here. Okay, now we will take into account all the measurements that we need to take. For the time, we'll come back to the time. Actually, yes, all right. Number N, number of turns counted using observation, plain observation. Okay. Area by measuring the diameter of the coil using vernier caliper. Area can be calculated as A is equal to pi d squared over 4, right? Not pi r squared, since we're measuring the diameter. Then what else do we have? Resistance R, using an ohm meter, using it outside the main circuit, or when no current is flowing, when no existing current is flowing through the resistor. So remember this. So whenever we need to measure the resistance of a resistor using an ohm meter, we do it away from the main circuit. So when existing current is flowing, it will alter the ohm meter reading. Okay, right. R is done. Length using a ruler. What else do we have? Supply voltage E. Oh, sorry, just E. By setting it with a power supply. And what else? There was one thing. Oh, time T. Sorry, V potential difference. Did we say what this is? Let's write over here. V PD V. Let's write over here. V by connecting an oscilloscope across the resistor. T we will measure by analyzing the history of the voltage sweep voltage curve from the oscilloscope. The time to reach maximum voltage or potential difference can be determined. The time for current to reach maximum is identical as the time to reach maximum potential difference across the resistor. Right, okay. Now we have done everything. What else do we need? What else do we need? What else do we need? Right, okay. Now we start off with a procedure. The procedure. So the power supply, okay. First we will measure the resistor. After measuring the resistance of a resistor, it is connected in series with the coil, switch, and power supply as shown in the diagram. The switch is turned on and the oscilloscope is set to record the signal. Okay. The history is analyzed and time to reach maximum PD across resistor is noted. And switch and power supply the power supply is turned on. Switch is then closed. Okay, now the history is analyzed and the time to reach maximum potential difference across the resistor is noted. This is repeated, this process is repeated twice, and the results averaged, and the time results averaged for this particular for particular resistance R. The experiment is repeated with all the unmarked resistors available while ensuring the coil uh, is allowed to cool during the breaks, in between the trials, in between experiments, in between measurements. Yeah, okay. So, right. The results are recorded in a table. Okay, now the analysis portion comes. Now we have to talk about how the table can be made. The table uh, could be, uh, wait, hold on. Drawn or made as follows. So you could have, for example, let's say we have the resistor R, ohm, then we have the time or the maximum potential difference, or either way it's fine. Even if you write the time t, t uh, per second, that is also fine. We don't need to include the other quantities because the rest of them are constant. But still, let's check what we can include. Actually, yes, we can. What we can do is we can include the readings before we can, average them. So copy, copy. Oh, sorry. Copy and copy, copy. Now for this particular one, we can use the average symbol over here. The average bracket, so that just to show that this was an average over here, average time, average of each reading basically. So this is T3, sorry, per second. This is T2 per second and T1, right. So this is the average of each particular experiment. Right, okay. Now we go on to the graph. Our graph is plotted with something on the y-axis and something on x-axis. This is what we have to decide now. Let's go back to the equation. T is equal to kn squared A over LR. So let's write over here just for our working. T squared, sorry, no, T is equal to, what was it? T is equal to kn squared. Okay, let's just simply copy this over here. So what we can do is we can make it into some sort of straight line equation because r is independent, t is dependent. So we can start with 1 over r. Right. Okay. So what we can do is we can include one more column for 1 over r. 1 over r, and that will be per ohm. Right. Okay. And then we have k n whole squared area. Oh, sorry, not this extra small n over L. That's it. Okay. Now on t per second is on the x-axis, and 1 over r, this is on the x-axis. So wait, what? One over r per ohm. So the units are very important. Okay. A best fit line. A best fit line is sketched. Okay. Right. Now, obviously, the hypothesis will only be valid if this indeed turns out to be best fit, if the best fit line can be drawn. Hypothesis valid only if a best fit line can be drawn we know in the statistics about the regression score. So if you want, you can write about that also. But either way, if you want to skip it, that's also fine. Okay, now we actually have to find out what k was, right? So just to make sure, we need to find a value of k, right? Okay, going back. So we need to tell what our gradient is and what our y-intercept is. So y-intercept is 0 over here. The gradient will be kn squared over kn squared a over L by calculating, by finding the gradient, sorry, or slope of the best fit line, or you can use the keyword gradient over here. K can be found by simply just use the formula right here, gradient times by L divided by n squared and a. Because L goes on to, because gradient is equal to, actually let's write gradient is equal to k n whole squared a over L. So now you can go back and figure out the k. Right, and that's about it. That's about it. Right, okay. Now the safety precautions. So safety precautions have to do most probably for the handling of the coil, because obviously when current is passing through this coil, it will get hot. So we will write careful handling of coil with gloves to protect against electric shock or burns. Okay. And what else can be used? What else can be used? Yeah, that's probably it. That's probably it. That's perfect. So just as a recap, just a very short recap, we have the power supply, switch, coil, resistor, storage oscilloscope for finding out the time, T, ohm meter for measuring the resistance outside of the main circuit. So first you measure the resistor and then plug it into the circuit. And we don't have to do this again. We don't have to count the number, length, and the diameter again and again. It's just one time. But we do have to describe actually the process. Otherwise, it will be incomplete. The essence of this is essence of your experimental writing over here, experiment writing is it should be reproducible by somebody. Okay, somebody else, some other scientist, some other friend, teacher, whatever. So it should be very clear in proper steps. So the methods of data collection should be very clear also. Procedure should be very clear and easily reproducible. Analysis part also, obviously it could differ from person to person, but you have to keep it very clean and easy to follow. And that's about it. That's about it. All right, let's move on to the 5.2 version of this session. Okay, so now let's see this 5.2 variant of the May-June 22 5.2 variant of it. Paper 5 question. Planning question, basically. All right. A student investigates the heating of a solid metal cylinder. Figure 1.1 shows the cylinder of the cross-sectional area A and height H. Okay. Student places the cylinder and an electrical heater in a beaker of water. Electrical heater is switched on and the student measures the time T for the temperature of the water to increase by delta theta. That means some degrees change. A number of cylinders of the same material but different cross-sectional areas are available. Okay. It is suggested that the relationship between T and A is this, where P is the power of the heater and W and Z are constants. Okay. Design a laboratory experiment to test the relationship between T and A, time and the cross-sectional area. Okay. You should draw a diagram on page 3 showing an arrangement of your equipment. Okay, all right. Let's go to the diagram and see how to make this. So this is the setup that I am using, and this is the diagram that I have drawn. As before, your diagram could be different. It could have lesser things over here, but I've just drawn it to illustrate everything I can. So for the measurement of temperature, we are using a thermometer. This is the cylinder. We're most often, whenever you use a heater, you will have to use the mains AC supply. And for measurement of the power, we have set our voltmeters and ammeters to read the RMS or VAC basically. Since it's going to be an alternating supply, we can't rely on the maximum or the lowest because it's alternating. So we deal with the average over here. So mean power. Vernier calipers and rulers are used to measure the diameter, which will lead to the area, cross-sectional area, and rulers are used for measuring the length or the height of these cylinders, right? Okay, all right. So let's go back and paste the equation over here so we can write the process over here. Okay, all right. So let's see. So we need the relationship between delta theta and power. Sorry, my bad. Sorry. Let's go back and see DNA. Sorry, time to for the water to temperature of the water to increase delta theta and cross section area. Sorry, my bad. T against A. Let me write over here T versus A. Okay. Okay. So independent variable is the cross sectional area A. Cross sectional area A of the cylinders. Okay. Dependent variable is the time T takes for temperature to increase by constant amount. Okay. Control variables, everything else will be controlled. Mean power supply, uh, AC power, AC power supply is going to be constant. That means the VRMS, VRMS. Similarly, the IRMS, right, which will control the mean power over here. The height h of the cylinder. This is already constant, so but we don't have to write it, but still you can include it. Delta theta, sorry, is the amount of temperature increase, in temperature. This is going to be constant. This is what we will have to control. And cross-sectional, cross-sectional area is the independent one. I hope I'm not missing out anything. W and Z are unknowns. W and Z are unknowns. Delta theta, we have already. Okay, all right. Now the methods of data collection. So methods of data collection, we had power by measuring the RMS or the root mean square of AC voltage and AC current. Mean power can be calculated, by measuring using voltmeter and an ammeter set to read in RMS. Mean power calculated by P is equal to IRMS times by VRMS. So this in subscript. Okay. This is for the power. What else did we have? Temperature. Oh, temperature. Oh, sorry, time. Oh, my bad. I forgot about the time. Sorry. So we should add a stopwatch over here. Let me just quickly add a stopwatch over here. Okay, so I've added a stopwatch over here to measure the time. Okay. Good. So time. So just t. So small t. Using a stopwatch. Okay. What else do we have? Area, cross-sectional area. By measuring the diameter of the cylinder using vernier calipers, cross-sectional area can be calculated as A pi d squared over 4. That's about it. Now the change in temperature, theta, or just theta, using a change in temperature. Oh, sorry. This was supposed to be with delta. Using a thermometer, any kind of thermometer, liquid and glass thermometer, or you could have an IR thermometer also. In my experiment, I have drawn the liquid and glass thermometer, but you could use the IR temperature gun also. Any other thermometer that you want to use, you can use that. We just want to measure the change in temperature. Okay, and what else? What else? What else? I hope I'm not missing out anything. Height. H. Uh, using a ruler to measure the height of cylinders. Okay. Right. Power, time, area, height, W, and Z are constants, right? What we need to know. Yes. Okay. Delta theta we have done. Okay. Now on to the procedure. You could add a switch over here also. You could add a switch over here for controlling the power supply. But if you're using the power supply, it will have its own functionality for turning it on and off. So that's on up to you. That's up to you. Okay. The equipment uh, is set up. No, sorry. First, we have to measure the cross-sectional area. The diameter of the cylinder of a cylinder is measured, and the corresponding area A, cross-sectional area A, recorded. Cylinder, heater, and a thermometer are placed in a beaker as shown in the diagram. The power supply is turned on and the stopwatch started. Okay, now the time t to reach a set change in temperature, delta theta again. I don't want to write it again, so I'll just copy it. Is noted and recorded. This is repeated twice, and time results averaged. Okay. What else we can do? Now we have to repeat this. The experiment is repeated with cylinders of different diameters. diameters, and the results tabulated. Okay, all right. Now comes the analysis. So we will justify this. This is already justified. Okay, all right. So the analysis, a table is used to record and analyze the record the data. Now the table that you can use is definitely going to be different than mine, but let's see how we can actually make it very easy to make over here. So area is the independent, right? So first off, we're measuring the diameter d. This is going to be in meters. uh, we can just keep it as d per meter. We then have area per meter squared, cross-sectional area meter squared. Then we have the time. I'll just copy this from the previous experiment that we just did. Because we're just averaging the time, and that's about it. So first reading, second reading, third reading, and the average time, average of that particular code. And then we will have different diameters and the same process repeated. And this is also in seconds, by the way. Sorry, let me go back and correct that one also. This is in seconds also. Okay, all right. This is okay, all right. Now, what else do we need to do? Yes. Now we need to come up with a way to actually graph it. So, graph is plotted with something on y-axis and something on x-axis. Now we have to decide what is going to be on our x-axis and what is going to be on our y-axis. So for that, what we'll do is I'll just simply copy this over here. To analyze this portion. Time is the dependent, right? So t is equal to area plus that. Okay. I will copy the delta theta. Where did I wrote delta theta? Yeah, because I don't want to do this again and again. This plus this. Okay. Now besides h, we have h. Sorry. H W delta theta a, and a is already there, so power comes in the denominator over here. And similarly, we have z, sorry, capital Z, and then power in the denominator. Just to make sure that we have everything, t can be on the y-axis. I'll use the average time that we just basically recorded. Okay. The final readings. We don't have to copy it, but that's what we mean over here. W and Z are unknown. Right. Okay. Now t per seconds is on y-axis and area per meter squared is on our x-axis. So the writing the units even this way is very important and marked, graded also, because if you're not clear about the units and are not very specific about it, you might lose marks. Okay, now we have to decide how we're actually going to find out the w and the z, right? The w is going to come from the gradient and z will come up from the y-intercept. So by finding the y-intercept, z can be calculated as by, or z equals to y-intercept times by t over delta theta. So because y-intercept is equal to z delta theta over p, so this will be the reverse of that process. Similarly, now we need to find out w by finding the gradient of this best fit line. W can be determined by, now we can write the gradient formula first, and then from that we can calculate the gradient. So W will be gradient times by power divided by h and delta theta. Okay, so gradient times by p divided by h and delta theta. That's about it. So we can forget about this. Right. So this is our W. So finally, we will say that our hypothesis valid only if the best fit line drawn can be drawn. Right. Okay. Now the safety precautions. So safety precautions have to do with handling of the heater mostly. Okay. So care must be taken not to the thermometer also, because if it has mercury, then that's poisonous for humans, poisonous for us also. So mostly it's about the power. So handling electric heater with caution, using gloves to protect against shocks and burns. Since we are putting this in the water, obviously steam is going to affect our vision, so we put on some glasses or goggles to protect eyes against steam, or simply just vision, you can say, against steam. Okay. What else can we do? I think that's about it. That's about it. All right, so this was pretty straightforward. Let's move on to the October-November papers. All right, so this is the October-November 21. Sorry, this is 21 and paper 5.1/5. Okay. A student investigates stationary sound waves in cylindrical tubes. Figure 1.1 shows a stationary wave pattern in a tube which is open at both ends. Okay, tube has length L, diameter D. The frequency of the sound for the stationary wave pattern shown is F. Okay, so if you notice, this is the fundamental note over here, or the fundamental frequency. This is the minimum stationary wave that we will get over here. Minimum frequency that we will, start getting a stationary wave over here. Fundamental frequency, fundamental note over here. So there are a number of different tubes available. It is suggested that the relationship between F and D is V over F is equal to 2L plus KD, where V is the speed of sound in air, K is a constant. Okay, all right. Design a laboratory experiment to test the relationship between F and D. F and D. F is the frequency, D is the diameter. Okay. Explain how your results could be used to determine the values for K and V. K and V. Right. Okay. So let's see our diagram, how we can actually set this up. Okay, so this is our diagram. One potential setup over here. So what I've done is arranged it vertically. You could do it horizontally also, or any other way you can choose. On a stand, I'm using three clamps over here, one to hold the speaker, one to hold the hollow tube, and one to hold the microphone. Speaker is connected to the signal generator with which we can control the frequency of the sound. Microphone is connected to the oscilloscope to monitor for resonance or the harmonics. Vernier calipers is used to measure the diameter D, and I forgot to draw it, but a ruler for measuring the length over here, length of the tube over here. But anyways, we don't need to draw everything. Okay, all right. So let me just quickly copy and paste the equation over here so we can start with the experimental design. Okay, and this is it, all right? So our experiment is for frequency versus the diameter. That means the fundamental frequency versus the diameter of the tube. Let's just make sure that I'm not wrong. Yes, F and D. All right. So independent variable is the diameter D of the tube. Dependent variable is the frequency, fundamental frequency. F. Okay. And control variables, everything else will be control. Length L of the tube. Speed of the sound we can't actually control, but we can control it with the temperature of the environment. Temperature of the surrounding environment. With a thermostat. Okay. Temperature of the surrounding environment, we know that if the temperature changes, the speed of sound will slightly change. With a thermostat, okay. All right. Now we go on to the method of data collection. Right. So we will go with the diameter D first. Using a vernier caliper. Diameter of the tubes can be measured. Okay. For like a better reading, you can measure measured in three positions at three locations. Can be measured at three locations. three positions along the length of the tube, along the length, and the result average. Okay. What else we can do? We have the frequency. Frequency, basically we're monitoring from the oscilloscope. Although we are adjusting it with the signal generator, but we are monitoring this from the oscilloscope. Set or adjusted from the signal generator. But the fundamental, no, actually, it's actually just simply just from that. Okay. But the fundamental frequency is only noted when oscilloscope, when resonance is observed or maximum amplitude is observed on the oscilloscope. Okay. Frequency F, sorry, that was just the note F. What else was there? D and F. L is the length. Using, okay, length of the tube is measured, sorry, using a ruler. Then what we have, so sorry, we have to, we have to tell how we are observed. Maximum amplitude is observed on the oscilloscope. Oh, I forgot about the microphone. Okay. So, but the fundamental frequency is only uh, for the frequency of sound, for the sound generated by speaker. But the fundamental frequency is only noted when resonance or maximum amplitude is observed on the oscilloscope as received by the microphone placed at the other end of the tape. Okay, all right. And what else do we have? Temperature. Temperature and fan speed are controlled using a thermostat and controller, speed controller, speed regulator, respectively, to keep the speed of sound relatively constant for the experiment. Because as we know, the speed of the wind and the temperature of the air will affects the speed of sound, although uh, even small changes, but we have to avoid that. Okay. Now procedure. Okay. Now procedure. So first off, we will set the equipment is set. Sorry, the equipment is set up as shown. with speaker and microphone placed at opposite ends of the hollow tube using clamps. The microphone is connected to an oscilloscope and the speaker connected to a signal generator. Alright. A set value for amplitude of input signal is selected and power turned on. The frequency is gradually increased while observing the response on the oscilloscope. When the resonance is observed, the frequency confirmed by signal generator and the oscilloscope suite, or you can say curve, oscilloscope suite, or reading, oscilloscope, is recorded. So this is repeated. Frequency is turned to 0 again. Is turned all the way to 0 hertz, and the process repeated twice, and the results averaged, and the results recorded or averaging. Okay. Next up, this experiment, the tube is replaced by another of different diameter, and the experiment diameter, let's say diameter already measured, and the experiment is repeated by, let's say, for example, you can say by others tubes of different diameters, and the experiment is repeated for each tube, and the results calculated. Okay, now moving on to the analysis. This was a basic procedure. Now the analysis. The analysis is that a table is drawn, or a table is drawn to record the results. Okay. So how will the table be drawn? We have the diameter. We have first reading of the frequency in hertz. Second reading of the frequency, third reading of the frequency, and one more for the average. So insert the right. And this I will choose to be in average bracket over here. Okay. So for each diameter measured in meters, obviously we will convert it into meters. Then frequency, repeated each time, and then okay. All right. So table is drawn to record the results. Now we will use the values using the values recorded in the table. A graph is plotted. A best fit. I'm sorry, a graph is plotted. A graph of best fit line is plotted with something on y-axis and something on x-axis. Now we basically have to figure out what is going to be on our x-axis and what is going to be our y-axis. So let's copy this over here. Okay. So frequency was our, oh sorry, what else we can do? Since we have the frequency, we are what we have over here, what we can do is we can, insert another, we can insert another to the right, which can record, you can say, the reciprocal of frequency. So this 1 divided by this, and that will record in hertz, hertz per hertz, basically. So like this. Right. Okay. So what we can do is we can rearrange this equation just to see you don't just to see how it becomes. V can be multiplied on the other side. So this becomes 1 over f 2L over V plus KD over V. Sorry, D K over V. Right, okay. So now we can delete this. So 1 over f can be on our x y axis. So actually, we don't need that. 1 over f in hertz minus 1 on the y-axis per hertz, and the diameter d meters, and on the x-axis. So this is our y-axis, and that is on the x-axis. Okay. Now we need to figure out. Sorry, this k was k was. We need to find out k and k and So as you can see, 2L over V is our y-intercept. By finding y-intercept of the best fit line, V can be calculated. So we can calculate it. So first off, we will write what y-intercept is actually equal to. Is equal to 2L over V. So V will be equal to 2L over y-intercept. Y-intercept. Now we need the other thing, the gradient for the K by finding the slope of the best fit line. K can be found. So we will write slope is equal to this thing K over. So K will be equal to simply slope times by V, which we have already found. Now the hypothesis will be valid obviously only if a best fit line is achievable. Okay. Now let's see what our safety precautions are going to be. Safety precautions over here. Safety precautions. Now, since this is sound, and obviously we're observing for uh, resonance, we have to use ear mufflers, and we can, keep the sound less loud. That means lower amplitudes. Okay. So, safety precautions. Ear mufflers can be used to protect against loud sound. Amplitude of the signal can be kept low enough to avoid loud sound. Okay, and that's about it. You can actually, there's no other thing that comes to mind about this. Right, okay, moving on to the 5.2 version of the October-November 2021. Okay, so moving on to the October-November 21 variant 5.2. Alright, so a student investigates the extension of a spring supporting a wooden strip as shown in figure 1.1. One end of the strip is at point P and the strip has length L and is at an angle of theta degrees, theta to the bench, whatever this is, L. Okay. The spring is attached to the strip by a wire at a distance D from point P, right over here. Okay. The spring has extension X. The wire is basically attached to the spring. Okay. It is suggested that the relationship between X and theta. X is the extension, theta is this angle over here, is given by WL and whatever this is, where K is the spring constant of the spring and W is a constant. So design a laboratory experiment to test the relationship between X and theta. So X is the extension, theta is the angle of the inclined plane. To explain how your results could be used to determine a value for W. Okay, all right, let's go to our diagram. Okay, now this is the diagram or the experimental setup that I'm using for this experiment. Okay, so what I have done over here is that there's a ruler attached with this same stand on which the other is attached to measure the height of this ring over here. That's that's determining this height of this spring attachment over here. The angles I'm measuring with two protractors joined over here to the wooden strips. One end of the wooden strip at P is joined with a hinge joint. The other is a normal joint, which is connected to the wire. The extensions we are measuring with just simple ruler. Okay. However, one thing which might be forgettable is we need a way to figure out the spring constant also. So spring constant, we will need another separate experiment to figure out the spring constant. All right, let's move on to the procedure. Sorry, defining the problem. Okay, all right. So this is our equation, which is what we are going to use to figure out all the variables over here. So our independent variable is theta, which is the angle between, sorry, angle theta between uh, between bench and wooden strip. And then dependent variable is our extension x of the spring. Control variables. Now, control variables, what we can actually control is uh, the angle beta. The angle beta. What else we can keep controlled? We can use the same spring. Okay. Keeping using identical springs. Using identical springs, ensuring they don't cross the elastic limit. For constant spring constant, basically. For constant spring constant. Ensuring they don't cross the elastic limit. Okay. What else can we keep controlled? That's about it. Okay. Now the procedure. Now, okay. So the method of data collection, right? Now the method of data collection. So we have angle theta and angle beta. Angles theta, beta, using protractors attached to wooden strip. Sorry, wooden strip and bench. Angle theta is, attached to the bench and then strip. And wooden strip respectively. Okay. What else do we have? We have L using meter rule or ruler, the length of wooden strip, sorry, is measured. And what else do we have? Extension x using a ruler to measure changes in length, measure change in, measure the difference in, measure difference in extended lengths and unstretched lengths. So basically, x is going to be L minus L naught, and, and this is L naught, and extended length L, and stretch length. Extension can be found by, can be calculated by Excel. Extensions can be, okay, and spring constant K. Spring constant is determined separately by observing extensions by adding small weights incrementally while keeping an elastic limit. A graph of force extension is used to ensure that elastic limit is not crossed, is not exceeded, and for calculating the spring constant K from the slope of linear portion. Okay. Oh, sorry, wait. Angle theta, we are measuring, I just realized, to bench and wooden strip. Angle beta, now we have to say why and how we are keeping it constant. Angle beta, oh, sorry, by measuring the sorry by adjusting the height h, angle beta can be kept constant, is kept constant, and confirmed by a protractor attached to a joint. I think I named that joint as C, as linked. Okay, all right. Now the procedure. Now the procedure portion of this experiment. This x is all x. All right. Now the procedure. Okay. The equipment is set up as shown. A small angle theta is given, the and then the angle beta and then the corresponding angle beta, and the an extension x noted. The angle beta is then kept constant throughout the experiment by adjusting the height h of the stand as in the diagram. Okay, all right. Then what we do, the angle theta is incremented by small amounts as the experiment repeated until height h can no longer be adjusted. Okay, so the values and the data is then recorded in a table. Okay, all right. Now comes the analysis portion of this. Now, in the analysis portion, we will talk about how the table is going to be made. A table is made to record the data. Sorry, to record and analyze the data. Okay. Now let's see what kind of table do we need. Let's add more columns into it. Let's add more columns. So what do we need? Angle theta, angle beta, and they're obviously sine and cos. So theta in degrees. Okay. Then we have beta also in degrees. Okay. Then what we have is sine theta. Wait, the question had cos theta and sine theta. Okay. So we will need cos of theta, cos of theta, again degrees. Then we have sine of beta, also in degrees. What else do we need? Extensions. Oh, sorry. Extensions recorded in meters. And what else is there? We can, find the extension by lengths. length meters. Now extension x can be L minus L naught in meters. So we can just per meters for each extension, basically what we can do. The units are very important over here. Okay, so is there anything left over here? No. Okay, all right. So now we need a graph. A graph is plotted with something on the y-axis and something on x-axis. Okay, so let's see what is going to be. So when we look at this expression, we were varying theta and x was our dependent variable, right? Just to make sure that that's what we did. Yes, independent variable was theta. So we will just rearrange it first and then put x outside as a subject of the equation. So we will have cosine of theta, and then we will multiply with everything. WL over 2k d sine of beta. So okay, so W L K was the small k, spring constant. D is the distance. Oh, sorry, I forgot about the D. D is using a meter rule or a rule. Okay. So L was our length. The length from joint P to C is measured. Okay. Right. So X can be on our y-axis. X is we are keeping this in meters, just to stay consistent with the SI units. And this is in this, and on the y-axis we can put in the cosine of theta. Cosine of theta, and this is in degrees. So on x-axis. Right. Okay. Now let's talk about how we're going to find out W. We are going to find out the W. Okay. So W obviously by finding the gradient. By finding the gradient of the best fit line, W can be found by, so first the gradient is equal to this entire thing. So therefore W will be equal to gradient times by now 2kd, this entire thing, divided by. Okay, now finally hypothesis only valid if a line of best fit can be achieved. Right, so this is our analysis. Okay. Now the safety precautions. For the safety precautions, what we can do. Safety precautions. Okay, so wait, sorry. We have to, one thing I realized, we have to keep the d distance constant also. Distance d also constant. So we are going to write constant also, and kept constant using a hinge joint at P and a regular joint with a wire with the wire at C labeled in the diagram. Okay, so we have to talk about the D also. Sorry, my bad. D should be labeled from P to C, distance between P and C. Okay. Right. Okay. So we were talking about these safety concerns. Safety concerns. So safety concerns could be, so wire and the hooks can be slightly sharp. So we can say handling wire and the joints carefully to protect against injury to eyes and fingers. And that's about it. That's about it. So we thought of everything enough. All right. Okay. So now moving on to the 2022 now.